Hey, what's up, folks? Welcome back to Advent of Code in F Sharp. Last time we left off day 21, part 1, where we were disintegrating bricks in a tower. And today I want to dive in again and solve part 2. So maybe a quick recap of what we did for part 1 and then what we have to do, and then we can dive into the code. So part 1 was we have a Jenga tower, and we need to figure out how many bricks we can remove without the tower collapsing or without any other block falling down. And we solved it by first building the tower, because those bricks needed to fall down Tetris style first, and then building a graph to solve the actual question. So building a graph that says this brick supports that other brick, and then we could, by removing nodes in that graph or edges in that graph, we could check for which bricks were safe to remove. Now for part 2, we are going to have to look for chain reactions. So we'll need to figure out the best brick to disintegrate. For each brick, determine how many other bricks would fall if that brick were disintegrated. So we need to recursively disintegrate bricks. No, we need to disintegrate one brick and then see how many other floating bricks would fall down. Sorry. So that's not really recursively. It's one disintegration, but we have to do the Tetris fall down again after that, and that's new for part 2. Okay, that sounds cool. That sounds actually be pretty doable with the functions and the algorithms we have right now. It won't be the fastest piece of code, but I'm hoping it will be enough. Maybe before we dive into part 2, last episode we were using Plotly, as you can see here, to plot our graph, and I don't know if I have an example of it. I don't think so, but I played around with it a bit to make it a bit more clean and a bit more easy on the eyes, so we can troubleshoot better. So this is my actual input. It's nonsense. It's a lot of Tetris bricks or a big Jenga cube. But for the example, at least it will help us out a bit. So let me show the example quickly. And this is all vanilla. So there you can see our tower. So this helps us visualize what's happening in case of bugs, because last episode we were a bit stuck. And the nice thing about this is Plotly. It's a Python library that's ported to .NET. And it works out of the box. You just give it some points, you can generate 3D stuff like this. It all renders nicely in the browser. So it's really cool for quick and dirty data visualization. Now that I'm saying this, I'm like interested in how they do it. Is it a canvas? Is it a vector graphics? Yeah, it's vector graphics. Cool. But it works really great for one-offs like this, or even for more complex charting. Anyhow, let's dive into part 2. So we need to figure out for every brick, once we disintegrate it, how many blocks will fall down. Cool. Let me copy paste my code so we can rip it apart for part 2. There we go. So this valid disintegration things is not needed anymore. We just have to disintegrate every block and then run another round of the fall algorithm, and we need to count the number of bricks that has fallen. We don't easily do that. Where do we fall? Where do we fall? This is where we parse our input. This is where we sort it. This is where we fall. We have a drop function. So this drop function takes a tower, which is a list of bricks, and it returns the tower, but it does not return like how many bricks it dropped. We could have it return the number of bricks. We could have it return the bricks that have actually moved, or we could just compare the before state and the after state and count how many bricks have moved. That could also work, and maybe that's even easier. Bricks don't really have an ID. The only thing we know about a brick is its location. So will it be that straightforward? Yeah, it'll be pretty straightforward, I'm guessing. So let's first try to disintegrate a brick in the example. So disintegrating brick A would cause all other 6 bricks to fall. Let's see if we can figure that out by using our current building blocks or current functions. So let's try to disintegrate brick A from the example and then have another round of drop. So we have our initial tower, that stays the same. I'm gonna leave everything as is, and I'm going to do 1 round of disintegration, that's this thing. But I only want to do it for the brick A. So this is my support, that's my graph that we made in part 1. It's a graph structure mapping bricks to brick lists. And here it says maps bricks to all bricks that support it directly. So the list is whatever this current brick is depending on. So if we have support, we can disintegrate a single block in it. What is brick A? What is brick A again? Brick A is the one with Z coordinate 1. So let's figure out brick A. It's whatever, tower, or let's look it up in support. I'm gonna grab it out of the tower. So tower. So brick is a tuple of tuples, 2 coordinates, and both of them are on the 1 for A, so this should give us our... Sorry? Okay, it was just a slow compiler. So this will give me brick A, probably. It's on 1, 2. Yeah, it's on 0, 2, sorry. So that's brick A, that's correct. And let's now disintegrate that brick. Yeah, so that works. Disintegrated. And now we need to, so this is the tower before this we fall down, and now we need to fall down. But now that I'm saying this out loud, this is a support, so that's that graph, but my fall algorithm works on towers, which is a list of bricks. So we kind of have to transform this back again to a tower of, so that's pretty easy. Let's write a function for that. Do we have a, nope. So let's write a toTower given a support, and that just says, okay, give me all the keys. And that's it. So that just gives me the list of bricks. They should be sorted. They should be sorted. In what direction should they be sorted again? By this brick bottom. So I'm gonna sort it again. So this should return a tower. My tower's data structure is not optimal because we have to do a lot of comparisons. I should have sorted the... I should have made it a bit more smart, but I hope that for our input it will work as well. So there we go, we dropped after disintegrating brick A. And now I'm hoping that we can compare... Oh, sorry, we have to drop. We have not dropped yet. So we have to drop... what are the input arguments again? I see tower and bricks. Okay, it's an accumulator, so empty lists. And our brick list is disintegrated, it's sorted, so it should work. Oh yeah, we need to tower it again. I wrote the function but never used it, that's cool, that's great. There we go. So this is our after disintegrate, no, dropped again, let's call it like that. We're just playing around right now. So this is dropping the tower again after disintegrating a brick A in this example. And now I'm hoping we can compare the original tower with the this tower, and we should figure out 6 bricks have changed. So let's say count differences in tower 1 and tower 2. And differences is literally figure out all the blocks in one of those that are not in the other one because the z coordinate has changed. So it's give me all bricks in tower 1 that are not in tower 2. Something like this. And then sum that up. Something like this. So it's dropped again. Count differences. Oh yeah, that takes 2. That takes two towers. So let's do the original tower and the dropped again tower. Oh, it's 0. That's not good. Let me do a quick check here. Are those towers the same? They are the same. Oh no. Oh, but A is in there. How can A be in there? Oh, yeah. What happens if we disintegrate? That brick is in there. No, that's not. Where does A come from? It's the only block at height 1. There is no block at height 1 in here. Why is this here? Huh? So I do support. Brick A should be in there. There it is. It's not resting on anything. It's resting on the floor. If we disintegrate brick A, which should be 101, 121, yeah, should not be in there. It does not appear to be in there. So why, if I 2 tower this thing, is this in there? Oh no, that's not. This is a different brick, sorry. Is it a different brick? Oh no. No. I don't understand. It's taking the keys. It's taking the keys. I am super confused. Let's render disintegrated. Let's make it visual. So I'm gonna write a render function. Which just does the thing and shows me my Chrome pop-up. That's all fine and dandy. It's F#, it's not a pure language like Haskell. You can do stuff like this. So let's render the disintegrated tower. That does not look correct to me. Why is there something at height 1? That does not look correct. Let's quickly see what disintegrating does again. So we disintegrate a brick, we take all other bricks. This is not doing a lot. Oh. Yeah. Disintegrating is removing it from the right hand of the map. It's not removing it from the left hand of the map. Actually, we can do that, right? Yeah, I think we can just get rid of that as well. So we can also remove the brick. Why is B not defined? Oh, sorry, yeah, it's brick. I was confused by this B in here. So yeah, this will work. My disintegration removed it from all the support, all the edges, but not from the vertices. So this should work better. Let's render our disintegrated thing again. Yeah, now we're at height 2. That is great. Now we're correct. Cool. Now we should see 6, right? 7. That's a shame. Oh yeah, one of the bricks got destroyed, so that's not in there. So we should get rid of that one. So this is the differences. Actually, let's write a different function. Number of bricks dropped. Nah, let's not. I know what I'm doing. It's this minus 1. So that's correct for brick A. Let's find brick. There was a second example, right? Let's find brick F. Brick F is the brick at height 4. So that should be brick F. Let me grab that one. It's 0, 1, 2, 1. Yeah. So we can do the same algorithm. I think this is our algorithm for part 2 in essence. So we disintegrate brick F. We drop everything again. We take a look at how many dropped. 1. Oh yeah, it's just the 1. Let's render just for funs. Yeah, there's something removed from line 4 here. Something's floating. Actually, is that correct? Dropped again? Oh yeah. Why am I rendering disintegrated? That was just to check stuff, right? This is the final tower where we dropped. Yeah. Ooh, that's a cool little brick tower here. But I think this is the meat of our algorithm. We just loop over every brick A and brick F as we did before, and we do this minus the rendering. We do this, so we can get rid of this part. We can say, okay, let's do part 2 given a tower. Or support. We start with support apparently. And that just does the thing. And it returns the number of dropped bricks. And we need to sum those for all bricks, right? So let's do... this is not exactly solving part 2, so this is a count number of bricks that would fall, that's a long name, after disintegrating brick. So yeah, this is where we're gonna get. I think this is the longest function name for any F# function I've written in my life. But I just want to get my stars, hopefully within a reasonable amount of time. So let's try this. We have our, this can go as well. We have our tower. Yeah, we have our initial tower. Let's build our support. We do that somewhere already. So yeah, it's this thing, support. So we have our initial support. And then we just need to loop over our bricks. So let's do that for tower again. It's a list of bricks. So for every brick, we want to count the number in the original support. And we want to sum that, right? So let's actually shift the order of these arguments. That's the thing that changes more often. And I put everything that changes more often in the argument list more to the right. And that way you can do stuff like this. Partial application, you don't need to write a fun lambda wrapper around it. It's just partial application of this function. And it's a bit of a cleaner read, I find. And we need to sum all those values. So this should be 7 for the example. I'm calling my shot. Kent Beck style, I'm counting my shot. So yeah, this is part 2. and it works for the example. So I'm hoping it'll work for our input, which is a huge tower. So let's put everything into place. Everything is in place. Let's see how long this calculation takes, because I'm pretty curious myself. It takes long. I was expecting it. Let's maybe take a look at my CPU. See if it's not burning up too bright. It's getting there. I might have to do this off camera because my computer does not handle intensive calculations and streaming at the same time. So what am I going to do? I'm going to stop. I am going to do a quick recap, and then I'm going to let this algorithm run for 5-10 minutes, and I hope it'll solve it by then. If it does not, we will do a recap or another attempt that is more performed, because we know what we built is not the best approach, but I was kind of hoping it would be enough. But maybe a quick recap of how I inefficiently tried to solve part 2 today, which was actually reusing all the building blocks we had for part 1, except we do, after we initially did a fall and disintegrate, now we do a fall, disintegrate, fall again, and we count like the differences. So it's using a bit more of that disintegration logic, or the falling logic, sorry, the drop. So here's me hoping this solved it in a reasonable amount of time. I will get back to you for the coming days, of course, and I hope to see you again for more Advent of Code in F#. Bye bye.